Well, the great part about this recording device is it only records this part of my screen, not all of the other crap that's going on. Okay, so this is the end of stuff we're learning here about, modern physics. So essentially, here, we want to see, or we want to talk about how this stuff applies to your life. So here we have a picture. What do you think this is a picture of?
Some cancer.
Tumor. So here, this is a picture, kind of, you can think of the X-ray part of the spectrum. Here it shows on the scan here, I think is it a PET scan? I can't remember. It might be a PET scan of a human body, right? Here you can see like higher concentrations, like here you can see like kidneys and stuff. But essentially what happens in this scan there is they give you something like, I don't know what that thing was, but essentially because tumors, like cancerous tumors, grow faster than the rest of your organs, if you give a material that's, used in making stuff grow, essentially the tumor will take it up more than the rest of the body. And if it's something that's radioactive, something that shows up on one of these scans, well, it kind of highlights it, just like you saw it. So here, this talks about carbon dating. So these are just different ways we can use radiation. Carbon dating is not where you take carbon out to eat. It's where we try to figure out how old an object is. Now we mentioned this before, that carbon dating is specifically talking about carbon-14. So carbon should have typically 12 things, 12 nucleons, so it's 6 protons, 6 neutrons in the nucleus. But carbon-14 has a couple extra neutrons, and eventually what happens to carbon-14 is it becomes nitrogen. And so what we can do is we can look at old material, like old organic material, like, in this case, the example is like an old tree branch. Maybe it becomes fossilized or something like that. You can dig it up, you can look at it, and you can look basically everywhere that should be carbon. You can say, oh, this isn't carbon, this is nitrogen, right? And there's a certain rate that carbon-14 is naturally created, and we think is relatively constant over time. And so essentially we look at it now and we go, okay, it's right now, this is how much carbon decay we're getting. So how much would that correspond to over the life cycle of this thing? We can figure out approximately how old it is. So for carbon-14, that's measured by beta decay. And so, it has a half-life of about 6,000 years. So, once you've got multiple half-lives, you can kind of calculate that out. So that's pretty good for organic material, because it's having a half-life of about 6,000 years means it's good for about 60,000 years of history. Now, in terms of organic stuff, that's pretty good. If you're looking at, whatever written record you're looking at, most of them don't seem to date back more than about 4,000 or 5,000 years. I'm not going to get into that much history, but that's essentially how carbon dating works. Does that make sense? Nuclear medicine. Nuclear medicine has many applications, and I believe a group picked nuclear as a presentation, so I'm not going to get too much into this. But essentially, nuclear medicine is anytime we use radioactive isotopes to help, heal a person. What I think is really interesting is when we talk about nuclear medicine, is that students are like, well, can't that give you cancer? Yeah, it can. So then the question becomes, okay, well, if doing some of these forms of nuclear medicine, if the possibility is that you get cancer, why would we use it? Well, it's pretty easy to see if you take a concrete example. So the concrete example I'm going to use is actually a what's called a swallow study. Now, because of my children and their unique perspective on life, some of my children have had to undergo what are called swallow studies. One in particular has actually done, I don't know, 15 to 20 swallow studies. So what is a swallow study? So that's essentially what you're seeing here in this picture on the slide. Then in a swallow study, they take the person, they take them to a room where they do x-rays. And instead of taking an x-ray picture, they take an x-ray film. And that person will, if they're doing a swallow study, they'll drink something that's radioactive. In the case of my daughter, she drank radioactive barium. Okay? She would drink it, and because it's radioactive, it will show up on the x-ray scans. Now the whole point of doing that is that when you take an x-ray, x-rays can penetrate soft tissue, but they don't typically penetrate bone. So they bounce off bone, and you get this reflection. And so what you're seeing in an x-ray is generally the dark areas are the areas that have been exposed, right? The photons of x-rays have passed through. And so that's where you get these dark areas here. The lighter areas are areas that, the x-rays have reflected off of, which is why you'll notice that when this person drinks the barium, it's very dark because it's putting off a bunch of x-rays. And so we can actually see that on the film because your esophagus and stuff wouldn't typically show up on an x-ray. But with a swallow study, you swallow it and then you kind of see what's going on here. And if you look carefully, because this is not the first swallow, you can actually see the esophagus here, and you can kind of see like the epiglottis, like right here in this area here. And so when you swallow something, you guys know that you have one throat, but there's two pipes, right? One for air, one for everything else. And so what happens here is when you swallow something, the epiglottis should close over your windpipe, allow the food or liquid to go down past that, and then open again so you can breathe. Right? Works pretty well. But in one of my daughters, she has an issue that when she swallows something, typically what happens is your esophagus squeezes the food and pushes it down, and squeezes it, pushes it down, all the way until it gets into your stomach. Right? She has an issue where her nerves don't quite work like they're supposed to, and as a result, when she eats something, her esophagus doesn't push above the food, it just kind of squeezes everywhere. And as a result, the food eventually goes into her stomach because, well, gravity pulls it down. But what can happen is, especially if she drinks something relatively thin like water, what would happen is like the food or water would get squeezed down past her epiglottis, past her windpipe, which would then open back up so she could breathe, but then it would squeeze from below and causing the food or liquid to go up rather than down. And if your windpipe's open, well, then it can cause the food or liquid to go into your lungs. Is that where you want food? No. Now, fun fact, if you get food or liquid in your lungs, your body will essentially, think of like digesting it out of your lungs, remove it. But are your lungs supposed to digest food? No. So it's not very good. So at first, your lungs typically like attack it. Because, it's a foreign substance. And so, in general, you can handle a little bit of food or water in your lungs. Your body will remove it. It's just not going to be a very quick process because let's just say your body does not expect that. But over time, that can lead to things like pneumonia, especially depending on the level of food or liquid in your lungs. So, the story that I've given you here, I've told you that my daughter has to undergo swallow studies to figure out what was going on. Because the whole point is without this swallow study here, we wouldn't know what was going on. When she was very, very young, basically she would just get deathly ill and be not able to breathe. And they'd be like, well, there's liquid in your lungs. And then we would take her to the hospital. They would suck out her lungs. And then she'd have to get a bunch of breathing treatments. And generally, when she was an infant, she would be in the hospital for like a month, like every December. Like I was lucky, I was teaching. I was lucky to get through the first couple of weeks, when we got to Christmas break. And usually the whole Christmas break, I was just in the hospital with her. Or at home because my wife was in the hospital with her. It took us several years to figure out what was going on because the doctors didn't know, nobody knew. We just knew December rolled around and her lungs sucked. Well, it turns out her lungs don't suck. They just had food or water in them. And that typically will, it decreases your ability to breathe. So when you look at stuff like nuclear medicine, people go, okay, well, isn't this barium radioactive? Yes. Can it cause cancer? Yes. Now, it's kind of like the x-rays. Like, if you just think about it like a regular x-ray, if you go get an x-ray taken of like your broken arm, get x-rays of your teeth, what's the point of that? Why do doctors take x-rays? So you can see the bones. So you can see what's going on inside. Now, when you actually stop and think about it, if you want to see what's going on inside of a person, let's say you don't use x-rays, what do you use? Yes, pretty much. And that's the trouble. Like, most doctors will tell you that surgery is kind of like your last option, right? They're going to try a bunch of other things because where a surgery might work, you might just go in with a scalpel, cut out whatever the problem is, and move on with your life. That does work. But the problem is whenever you have surgery, there's always the possibility of complications of surgery, right? No matter how simple or complicated the surgery is. And basically, hopefully you don't have one of those horror stories where the surgeon leaves something in you. But typically, we're pretty good in this country about doing pretty good surgeries, keeping everything clean, making sure everything's connected back where it's supposed to be. But the whole deal is that sometimes things happen. And the thing is your body doesn't like to be cut open, believe it or not. The whole deal is we try not to cut people open as much as possible, in general. Because your body doesn't tend to necessarily recover how we think. And so by using things like x-rays or PET scans or whatever, we can look inside your body without having to cut it open. Now, every single one of these scans involves something like x-rays or gamma rays or something like that. Usually not gamma rays. Hopefully not gamma rays. But the whole deal is that will, again, give your body some risk of cancer. Now, we believe that the risk of cancer is pretty low. Like for a typical x-ray, I don't know the statistics, I'm sure you can look it up. But the odds of you getting cancer from one x-ray are very low, as to be basically zero. Now, is it zero? No, which is why the doctor's like, oh, when you get an x-ray, they're like, okay, let me take this x-ray, it'll be fine. For you getting exposed to an x-ray, once every year or once or twice, a couple of times a year is it's basically negligible, compared to the natural background radiation. But it's not zero. And so the more you do it, like if you drink barium and get a radioactive or get an x-ray video taken of you, the odds are a lot higher. But again, you have to contrast those odds with either A, not knowing what's going on, or B, cutting the person open. And the odds of something happening when they cut you open are far greater than the odds of cancer from any of these treatments. Does that make sense? That basically with my daughter, I can speak from this experience, we had no idea what was going on for years. But now that we know this is the problem, and we've been able to adjust things, like for the longest time, she had to drink thickened liquids. Like we had to thicken it so it wouldn't go into her lungs. Once we started doing that, she basically doesn't have to go to the hospital anymore. I mean, occasionally people go to the hospital for normal reasons, but she typically doesn't go to the hospital nowadays, which is a huge improvement from spending a month in the hospital every year. So that's just one example of nuclear medicine. There's many other things here. Like I said, I just have some personal experience with the barium swallow, but I do want to address that because people are always like, well, what? So I voluntarily allowed people to give my daughter radioactive fluids and subject them to x-rays. Which if you contrast that with like today's debates about, are vaccines safe? Like, this seems hugely unsafe compared to vaccines. I know the risks, probably better than most, and I completely agree with them. Could she develop cancer from this down the road? Yeah. But without these treatments, she may have died already. So I'm contrasting her getting cancer when she's 40, 50, 60, possibly, with her just not living that long. Well, I'll take those risks. So how do we know if cancer is going to develop? Well, you don't. And that's one of the things that makes radiation poisoning, radiation sickness so tricky. Because first of all, very few people have actually been exposed to enough radiation to kill them. And in pretty much all of those cases, we don't know how much that radiation was. Because it was an accident. It was just like, oh, blew up in your face. And since we haven't deliberately exposed people to radiation, we don't know exactly how much it takes to kill you. Which sounds like a bad thing because we don't know, but it's a good thing because we didn't deliberately expose people to radiation, right? So when it comes to radiation doses, there's many units that people use depending on the country and all this stuff. I mean, obviously there's the metric, standard, but a lot of people and places don't use that. And unfortunately, the standard units are the common ones that you see nowadays. So like if you look up stuff, you'll see metric units. But unfortunately, most people are exposed to radiation stuff, not from scientific sources. You're exposed to news or video games or some crap like that, where they don't have to use any sort of standard units. So it can be really hard to look at it. Or if you're looking at it from a historical standpoint, obviously they used different units back then, which actually wasn't that long ago. So the biological effectiveness of radiation depends on how much energy was absorbed by the body and how the tissue reacts to that particular type of radiation. So there's two things going on here. It's A, the amount of energy, and B, the type, right? Because some types are easier to deal with than others. So we define radiation dose as the energy from ionizing radiation absorbed by 1 kilogram of tissue. All right. The SI unit of the dose is called gray, abbreviated GY, gray. So 1 gray is 1 joule per kilogram of absorbed energy. That seems pretty straightforward. A gray, getting 1 joule, first of all, is a joule a lot of energy? Not really. But in terms of electron volts, a joule is a lot of energy, right? In terms of ionizing energy, remember it took like 13.6 electron volts to ionize one electron from your hydrogen. And 1 electron volt is 1.6 times 10 to the 19th joules, so it's a lot. Sorry, 1 joule is 1.6 times 10 to the negative 19th electron volts. So it's a lot in terms of radiation. The relative biological effectiveness, RBE, is defined as the biological effect of a given dose relative to the biological effect of an equal dose of X-rays. So X-rays is like our standard, okay? It's our meter standard, so-called. So X-rays have a relative biological effectiveness of 1. It's defined to be 1. So gamma rays and beta typically are about 1 as well. You'll notice that protons have a biological effectiveness of 5, neutrons 5 to 20, and then alpha particles are 20. So the most dangerous type of radiation is alpha particles, okay? Because it says right here, the radiation dose equivalent is a product of the energy dose in gray, and then times this factor here, depending on what it is, measured, and it's measured in sieverts. So most things that you see nowadays are measured in sieverts. So essentially, if you have a detector that can detect the type of radiation, it can detect the energy and then the type, what caused this ionization, then you can get sieverts. For the Geiger counter I have up here, the Geiger counters only detect that there's enough energy to cause an ionization to occur. They don't know what type of energy made it happen. So Geiger counters just beep. That's literally all they do, is they beep. And they have different tones, and they can beep different ways, but that's all they do. And essentially, if you knew how many beeps per second, you could use that to calculate your gray. But in order to find the sieverts, you have to know what type of radiation caused that, right? You need a little bit more sophisticated type of sensor. For instance, most Geiger counters, like that one that I had in here weeks ago, that one I think costs like $50. But like a good one that measures in sieverts is usually like $700 to $800, because there's a lot more things that are needed to make that happen. Let's just say it that way. So does that kind of make sense? That like we know how much energy is happening, and then we multiply it times this biological effectiveness, right? Most things are just one. You say no.
Yeah, I don't understand why gamma rays and X-rays are equal if gamma rays are more powerful.
Well, they're more powerful, but they're going to do basically the same amount of damage. Technically, there's more energy in the gamma rays, and so you would get more sieverts from the gamma rays than you would the X-rays. But that would be in the gray part, not in the biological effectiveness. So essentially, if an X-ray passes through you, the damage it can do is it could like cut your DNA. Well, it's basically the same thing that the gamma ray would do, is would cut your DNA. Whereas like if an alpha particle hit, it's not going to cut your DNA, but it's probably going to completely destroy that cell. So, you know, it's like a bullet versus a hammer. Like the bullet can like cut things or poke holes in things, but like the hammer will just smash everything. So like the whole deal is, the reason why this is only like one up here is because if a piece of your DNA gets cut, your cell can repair it. It may not, or it might repair it wrong. But it can probably repair it. But if you just smash the cell, it can't repair itself. It's dead now. See the difference? That like this may or may not kill the cell, this definitely will. But it usually will only kill like the top layer cells. Probably the one cell it killed. So, you know. Does that make sense? Okay. So radiation dose. What's a safe exposure? Don't really know. So in order to kind of think about a safe exposure, we compare it to background radiation. We go, okay, well this is what's typically happening, you know, given like a whole, let's say, year of life here on Earth. And so we compare, you know, what you're getting to natural background, right? So you're always exposed to radiation from cosmic rays, radioactive atoms in the ground, and the food, and the atmosphere, all of this stuff. So that's our natural background. And so here, like a PET scan, it gives you 7 millisieverts. Natural background radiation gives you about 3 millisieverts. So a PET scan is like almost 2 years of living here on Earth. So for those of you who don't know what a PET scan is a positron emission tomography scan. And what it is essentially they use different rays, and they want to use positrons, like electrons and positrons, in your body. And when they electron and positron get together, they will annihilate and create gamma rays. And they pick up the gamma rays in the detector to make a picture of what's going on. Anyways, mammogram, that's where you get scanned on your chest. That's 0.7, so far less than what you would experience when you're here. The typical chest x-ray, you know, going all the way through, is about 0.3. Transatlantic airplane flight, so flying across the Atlantic, you get exposed to 0.05. And then a dental x-ray is 0.03. So those are just some typical things compared to the natural background. This is why we say, okay, this stuff is pretty low, because yes, there is a risk of cancer, but you know, just being here on Earth is a risk of cancer. So here's an example here. I'm not going to go into the meat of this, because sieverts and everything is not tested. So for example, it's like, okay, you have a 75 kilogram patient, and we're going to do a bone scan. So a phosphorus compound containing the gamma emitter techronium-99 is injected into the patient. It's taken up by the bones and emitted. The emitted gamma rays are measured. The procedure exposes the patient to 3.6 millisieverts of radiation. What is the total energy deposited in the patient's bodies in joules and electron volts? So here, you know, essentially we can know these things like, okay, I'm going to inject this much techronium, and this much techronium-99 when it decays should give off this much millisieverts. Techronium-99, I think, has a really short half-life of like an hour or something, or less than an hour. Because I think like after a day, It's essentially inert. So here you take your sieverts. Remember, sieverts is your dose in gray times your relative biological effectiveness. In this case, your relative biological effectiveness is 1, because it says gamma rays, right? So the number of sieverts is 3.6 millisieverts, so that would end up being the same as your dose in gray. So gray ends up being 3.6 millisieverts. Everybody okay with that? Because the relative biological effectiveness is 1. So then to find the energy, what we have to do is we take our gray, which is joules per kilogram, and we multiply it by the number of kilograms of the person's body. So this person receives about 0.27 joules of energy from this one dose, which again, joules are not very big. So this isn't very much energy over his whole body, but you have to remember in terms of ionization energy, it's actually a lot. And so here we convert the last answer to electron volts, so that's about 1.69 times 10 to the 18th electron volts. So certainly a lot of action can happen down on the subatomic level. Make sense?
Why is it your whole mass? Why are you multiplying by your whole mass if you're just doing a bone scan?
Well, because you're scanning the whole body, and when you inject something into the bloodstream, it goes everywhere. Now it should theoretically get taken up by things that are causing cancer and be concentrated in those areas more. But basically we can't predict what areas are going to get more radiation than others, because even though it's going to take up most of the material, it still might have given off more of the radiation in another part of the body before it got there.
So if you were gonna take an X-ray of one bone, then it would be.
Well, this isn't the same as an X-ray, because it's kind of like an X-ray, but we injected it with material.
Okay.
If you're doing just an X-ray and you're like, okay, how much is that? Then yeah, you could just do like that particular part of the body.
Okay.
Does that make sense? But yeah, this is just, we're injecting stuff into you, so yeah, it's going to go everywhere. So again, you compare this energy to how much energy it causes to do things. So like breaking a hydrogen molecule, energy released in one molecule of ATP, or the energy needed to ionize a hydrogen atom. You'll notice that this number of electron volts that we put into the person is significantly more than any of these. So. Here, nuclear medicine, the tissues in the body that are most susceptible to radiation are those that are rapidly proliferating, so things that grow more. So radiation therapy applies a large dose of radiation to destroy or shrink a tumor while attempting to produce minimal damage to the surrounding healthy tissue. So like chemotherapy, things like that. Other tumors are treated by surgically implanting low energy radioactive seeds within a tumor. They will sometimes physically put radioactive material in you because it'll put off a lot of radiation, but they'll put it inside the tumor so it'll radiate it from like the inside out. Because the problem is, when it comes to tumors, ideally what you'd like to do is cut out the tumor. However, we're talking about things on the cellular level, and it's really hard to cut at the cellular level. So as a result, typically when you surgically remove it, they try to take out a larger chunk, right, to make sure you get all of the bad stuff. And even in that, sometimes you still miss it. And if it's a sort of a little, if it's small to begin with or in a weird spot, it might be easier to do this. I'm not a doctor, I'm not going to tell you what you should or should not be doing. Some tissues preferentially take up certain isotopes, allowing treatment by isotope ingestion, a common treatment for hypothyroidism. So if you have like a thyroid that's overgrown, they can give you iodine-131. What ends up happening is that the tumor wants to take up this iodine, but because it's radioactive, it will actually destroy the tumor. So it'll reduce the gland's activity with minimal disruption to the surrounding tissue, because most of that stuff given off is, again, almost immediately absorbed by the tissue around it. If the tissue around it's all tumors, well then that's a good way to kind of knock it down. Nuclear imaging. Nuclear imaging uses radiation from isotopes within the body to produce an image of tissues in the body. So an X-ray is an image of the anatomical structure, while nuclear imaging produces an image of the biological activity of tissues in the body. So that's an important difference. That literally what you're seeing in a nuclear picture is you're seeing the actual body like undergo, like do its biological stuff. Like think about like ATP becoming ADP and stuff like that. A gamma ray camera can measure and produce an image from gamma rays emitted within the body. To use a gamma ray camera, a patient is given a compound, usually like tacrolium-99, which is taken up by bone tissue where active growth is occurring. The camera can then pinpoint the location of the gamma emitting isotopes. So here it kind of shows you like, you'll have like, okay, we want to look at what's going on right here. So you have your, sensor array. And basically as the stuff comes off, we can detect it here, these sensors, but notice that there's like a culminator. So that there's like a bunch of lead plates that essentially, unless this thing is going pretty straight up, these gamma rays are going to get absorbed by the lead plate and not make it to the sensor. Does that make sense? Which is why the computer can kind of map like what's going on directly below each sensor as opposed to the stuff coming from the side. Because can we predict what direction these photons are going? No. But by putting something like this culminator in the way, we can break down the angle to being pretty straight. And so then the sensors here will kind of notice when they get that much energy, and they'll report that to the computer, and the computer draws a program saying, okay, we're getting a lot of activity here and there, and not so much in these other areas. Does that make sense? So here's the image produced by gamma ray camera, highlights areas of active growth. These bright spots show active tumor growth. Because like they're taking the tacrolium-99 more than other things. Example 2, a patient suspected of having kidney disease is injected with a solution containing molecules that are taken up by healthy kidney tissue. The molecules have been tagged with radioactive tacrolium-99. A gamma camera scans the patient's abdomen and gives the image below. In this image, blue corresponds to areas of highest activity. Which of the patient's kidneys has reduced function?
I wonder if it was smaller.
I wonder. The smaller one, maybe? Yes. And so, like I said, it's one of those things that, it will expose the patient to some radiation, and you can calculate how much that is. But again, knowing that the left one isn't working as well as the right one is something to note. Because, if you're going to go in and, let's say, take out a kidney, you want to make sure it's the right one. In this case, the left one. So positron emission tomography, PET, which I mentioned earlier. Most PET scans use a fluorine isotope, like 18, fluorine 18, which emits a positron as it undergoes beta plus decay to become oxygen. It has a half-life of 110 minutes. Fluorine 18 is used to create an analog of glucose, which gets taken up by the brain and gets concentrated in active brain regions. So PET scans are used typically on your brain. And so here, basically it emits a positron, and then when the positron combines with an electron, it creates those gamma rays that we talked about earlier. But notice that it will create 2 photons, but they'll be going in opposite directions. And so we put this detector all around your head, and they can pick up the 2 positrons on opposite sides, and they can trace them back to where they came from. Because if one gets there sooner, then it's more on the left side than the right side and all that stuff. Yeah. And so that's one of the reasons why we have or we're able to do brain scans. Again, you have to give them some fluorine and stuff beforehand. Because it's one of those things that if you want to be able to measure things, how is their brain responding? How do we know this region of the brain is responsible for unfamiliar language or whatever? This is how we get some of those things. So this is the last picture here, so we're going to stop here today. So like I said, those notes aren't terribly long, and they're not terribly tough. And most of the examples in there you don't need, but again, I want to connect what we're learning to the real world.